Are you preparing for your next generative AI or large language model interview? In today's video, I've got you covered with the top 150 unique LLM interview questions and answers explained in clear, just like you deliver in a real interview. We'll cover everything from fundamentals and architectures to prompting, fine-tuning, real-world applications, and future trends. By the end of this video, you won't just know the answers. You'll know how to explain them with confidence, so stick around till the end. This could be the difference between a good interview and landing your dream AI job. What is a large language model, LLM? Think of an LLM as a text prediction engine on steroids. It's trained on massive data sets with billions of parameters to model the probability of language sequences. Unlike narrow NLP models, it's general purpose, capable of translation, reasoning, summarization, or even coding. GPT, LLAMA, and Falcon are prime examples. In short, LLMs transform raw statistical learning into human-like language generation across tasks. How do LLMs differ from traditional NLP models? Earlier NLP models were specialists. They relied on handcrafted features or limited data for single tasks like sentiment analysis. LLMs are generalists, trained on diverse text at scale, using transformers for context. For instance, BERT was trained for mask prediction, while GPT-4 can write code, draft legal text, and answer questions, all without task-specific retraining. Scale and adaptability are the game changers here. Why are transformers critical for LLMs? Transformers solve the two big NLP problems: context and scale. Self-attention lets every token look at every other token, capturing long dependencies. Unlike RNNs, they process sequences in parallel, making billion-parameter training feasible. This efficiency and context modeling power are why GPT-4 and PALM exist today. Transformers made them possible. What is tokenization and why does it matter? Tokenization breaks text into pieces the model can handle. Unbelievable might split into believe, able. This reduces vocabulary size while covering rare words. Poor tokenization leads to inefficiency or lost meaning. Methods like byte pair encoding or sentence piece ensure models handle multiple languages and unseen terms effectively. It's the very first step of speaking the model's language. How do LLMs understand language? They don't understand like humans. They model probabilities. If you ask, the capital of France is, the model assigns high probability to Paris. After training on trillions of tokens, these probabilities align with human-like understanding. It's statistical pattern recognition, not cognition, but it's powerful enough to mimic reasoning, storytelling, and problem-solving. Difference between encoder-only, decoder-only, and encoder-decoder models? Encoder-only, like BERT, excels at understanding, classification, search. Decoder-only, like GPT, is great for generation, chatbots, coding. Encoder-decoder, like T5 or BART, shines in transformation. Translation, summarization. Think encoder equals reader, decoder equals writer, both equals translator. What is fine-tuning and why is it important? Fine-tuning adapts a pre-trained model into a domain expert. For instance, MedPalm fine-tunes general LLMs on medical literature, while Bloomberg GPT fine-tunes for finance. Instead of retraining from scratch, fine-tuning reuses general knowledge and sharpens it for specific use cases, making LLMs practical for real industries. What is RLHF and why is it used? Reinforcement learning from human feedback aligns models with human preferences. After pre-training, humans rank outputs, and reinforcement learning optimizes toward those preferences. This turned raw GPT-3 into ChatGPT, safer, more helpful, less toxic. Without RLHF, LLMs are fluent but unpredictable. With it, they become reliable assistants. What is Retrieval Augmented Generation, RAG? RAG gives LLMs a memory boost. Instead of relying on internal knowledge, they retrieve external documents using embeddings, then generate answers. For example, enterprise bots use RAG to pull from company policies. It reduces hallucinations and makes answers factual, up-to-date, and domain-grounded. It's like giving the model Google inside its brain. What are hallucinations in LLMs, and how are they mitigated? Hallucinations are confident but false outputs, like citing fake studies. They happen because models predict words, not truth. Mitigation involves grounding via RAG, reducing randomness with lower temperature, and post-checking with human or symbolic systems. In mission-critical domains, hallucination management is as important as accuracy. What is the self-attention mechanism, and why is it important? Self-attention is the heart of transformers. It allows every word to look at every other word in a sequence and assign weights. For example, in the dog chased the ball because it was hungry, the model learns it refers to dog. This dynamic context modeling is what makes transformers and LLMs so powerful compared to RNNs. Without self-attention, large-scale coherent text generation wouldn't be possible. What are positional embeddings, and why do we need them? Transformers don't naturally know word order. They treat input as a bag of tokens. Positional embeddings inject sequence information so that man bites dog isn't confused with dog bites man. They're added to token embeddings during training. Without them, transformers would lose the very structure of language. In short, embeddings give meaning, positional encodings give order. How is an LLM trained from scratch? Training starts with massive text datasets, web pages, books, code. The model is initialized with random weights and trained with self-supervised tasks like predicting the next token. Gradually, billions of parameters adjust through gradient descent. Because these models don't fit on one GPU, training uses distributed clusters of thousands of GPUs with weeks of compute. That's why companies like OpenAI and Google spend millions building frontier models. Can you compare encoder-only, decoder-only, and encoder-decoder models? Think of them as readers, writers, and translators. Encoder-only models like BERT are readers. They excel at understanding and classification. Decoder-only models, like GPT, are writers. They excel at open-ended text generation. Encoder-decoder models, like T5, BART, are translators. They read input and generate structured output, great for summarization or translation. The architecture you choose depends on whether the task needs understanding, generation, or transformation. What is perplexity, and why is it used to evaluate LLMs? Perplexity measures how well a model predicts a sequence. A lower perplexity means the model assigns higher probability to the correct words. For example, a medical model with low perplexity on clinical notes shows strong predictive power. But perplexity isn't perfect. It doesn't always match human judgment of quality. That's why newer benchmarks like MMLU or Big Bench are also used alongside perplexity. What are attention heads in transformers? Multi-head attention is like having multiple readers analyzing a sentence from different angles. One head might link book with table, another links book with mine. By combining them, the model builds a rich contextual understanding. It's not one lens, but many. And that diversity of perspectives is why transformers can model nuanced relationships in text. What are gradient checkpoints, and why are they important in training LLMs? Gradient checkpoints are a memory-saving trick. Instead of storing all intermediate states during the forward pass, only key ones are saved and others are recomputed during backprop. This lowers GPU memory usage, allowing us to train much larger models. The trade-off is more compute per step, but without checkpointing, billion-parameter models wouldn't fit into GPU memory at all. Why is distributed training essential for LLMs? A single GPU can't handle models with hundreds of billions of parameters. Distributed training splits the work. Data parallelism replicates models across GPUs. Model parallelism splits layers, and pipeline parallelism staggers computation. Without these techniques, training GPT-4 or PALM2 would take years instead of weeks. Distributed training is the engineering backbone that makes LLM scaling possible. How does fine-tuning differ from pre-training? Pre-training is broad learning on massive, diverse datasets. It gives general knowledge. Fine-tuning sharpens that knowledge for specific tasks or domains. For example, GPT-3 pre-training gave general language ability, but fine-tuning produced codecs for programming. Pre-training builds the foundation. Fine-tuning customizes the house for your use case. What are embeddings and why are they powerful in LLMs? Embeddings are dense vector representations where meaning is encoded in geometry. Words with similar meanings, king and queen, are close in vector space. This allows semantic search, clustering, and retrieval augmented generation. Embeddings are powerful because they translate messy human language into math that machines can reason with, making them the hidden workhorse behind most LLM applications. What is zero-shot prompting? Zero-shot prompting is where the model has to figure it out with no examples. For instance, you might say, translate good morning into Japanese. The model relies entirely on its pre-training knowledge to respond. It's powerful because you don't need to prepare data or train the model, but results can be inconsistent in niche domains. Zero-shot is essentially testing the model's raw general intelligence. What is few-shot prompting and how is it different? Few-shot prompting gives the model a couple of examples before asking the real question. For example, show 3 English to Spanish translations, then ask for a fourth. The model sees the pattern and applies it. Unlike zero-shot, which depends purely on training, few-shot leverages in-context learning. It's like teaching a student with a quick demo before the test. It improves reliability, especially for structured tasks. What is chain of thought prompting and why does it help? Chain of thought is like telling the model, show your work. Instead of jumping straight to the answer, you ask it to reason step by step. For example, in a math problem, it might outline the formula and calculation before the solution. This often boosts accuracy because the model processes reasoning paths explicitly. It's particularly effective in logic, math, and coding, where structured thinking matters. What is instruction tuning? Instruction tuning means fine-tuning a model on data sets of instructions and responses. For example, summarize this paragraph. Here's the summary. This changes the model from a text predictor into an instruction follower. Without instruction tuning, outputs may be fluent but not aligned with user intent. With it, models become assistants, more responsive, reliable, and conversational, as seen in ChatGPT. What is RLHF and why is it critical? Reinforcement learning from human feedback ensures LLMs align with human values. After instruction tuning, humans rank model outputs. The model then learns to prefer responses people like. This process makes models not only factually correct, but also polite, safe, and useful. For instance, it prevents an assistant from giving harmful advice. Without RLHF, models may be smart but socially blind. With it, they feel human-centric. What are system prompts and how do they shape LLM behavior? System prompts are hidden instructions that set the model's personality and tone. For example, you are a friendly tutor who explains step by step. While the user never sees them, they guide behavior behind the scenes. This is how the same LLM can act like a lawyer in one app and a teacher in another. System prompts are the invisible hand shaping the model's voice. What is prompt engineering and why has it become important? Prompt engineering is the art of asking better questions. LLMs are sensitive to phrasing, so designing prompts strategically can drastically improve outputs. For example, saying, explain quantum computing to a 10-year-old yields a very different answer from define quantum computing. It's important because it lets you guide model behavior without retraining, making it a low-cost, high-impact way to get reliable results. What are embeddings-based retrieval methods in LLMs? Embeddings convert text into vectors in a high-dimensional space. Similar vectors are close together, which makes semantic search possible. In LLMs, embeddings allow retrieval-augmented generation. The system retrieves relevant documents and feeds them to the model for context. This powers enterprise assistants that answer from company data or chatbots that stay fact-grounded. Embeddings are the bridge between raw text and factual, context-aware answers. What is parameter-efficient fine-tuning, PFT, and why is it valuable? PF techniques like LoRa or adapters fine-tune only a small slice of model parameters instead of all billions. This makes customization faster, cheaper, and possible on modest hardware. For example, instead of retraining a llama entirely, you can fine-tune just 1 to 2% of weights for a healthcare chatbot. PEF democratizes LLM fine-tuning. enabling startups and researchers to specialize models without massive compute budgets. What is the role of temperature in LLM inference? Temperature controls how creative a model is. A low temperature, like zero point 0.2, makes outputs deterministic and factual, great for legal or medical use. A higher temperature, like zero point 0.8, makes answers more diverse and imaginative, perfect for storytelling. Essentially, temperature is the creativity dial. Turn it down for accuracy, up for creativity, depending on the use case. What are some real-world applications of LLMs? LLMs are already everywhere you look. In customer service, they power chatbots and voice assistants. In healthcare, they summarize patient records and draft clinical notes. In finance, Bloomberg GPT analyzes reports and market data. Developers use Copilot for coding, while students use models for tutoring and summarization. Essentially, anywhere language is used, law, education, research, search, LLMs are transforming workflows by making them faster, smarter, and more accessible. How are LLMs used in coding assistance? Coding is one of the clearest LLM success stories. Tools like GitHub Copilot and ChatGPT can autocomplete functions, suggest fixes, or even explain complex code in plain English. Developers can paste an error message, and the model proposes a likely solution. This accelerates development, reduces debugging time, and lowers the barrier for new programmers. In effect, LLMs act like an AI pair programmer, always available. What is Retrieval Augmented Generation, RAG, and how is it applied? RAG is like giving LLMs a live reference library. Instead of relying only on what they memorized during training, they fetch documents from a knowledge base, then generate grounded answers. Enterprises use RAG to build chatbots that answer from internal policies. Research platforms like Perplexity AI use it to provide cited answers. The result is fewer hallucinations and more accurate, verifiable outputs. How are LLMs applied in healthcare? In healthcare, LLMs reduce administrative burden and support clinicians. They generate discharge summaries, simplify medical jargon for patients, and assist in literature reviews. Models like Google's MedPalm are trained specifically for medical question answering. While they don't replace doctors, they act as intelligent assistants, saving time and making healthcare more patient-friendly. The key challenge here is safety and compliance with medical standards. How are LLMs transforming the legal domain? Legal work involves massive text, contracts, case law, compliance rules. LLMs help by reviewing documents, highlighting risky clauses, and summarizing lengthy filings. For example, an LLM can process a 100-page contract in seconds, flagging inconsistencies. This doesn't replace lawyers, but it augments them, letting them focus on strategy instead of paperwork. Many legal tech startups are already embedding LLMs to cut time and costs in due diligence. How do LLMs enhance search engines? Traditional search gives you links. LLM-powered search gives you answers. By understanding user intent semantically, they generate conversational summaries. For example, Bing Copilot or Google's Search Generative Experience combines retrieval with LLMs to give contextual cited responses. This transforms search from keyword lookup into interactive dialogue. Faster, more intuitive, and closer to how humans naturally ask questions. What are agentic LLMs and how are they applied? Agentic LLMs are not just talkers, they're doers. By integrating LLMs with APIs, tools, or memory, they can take autonomous actions. For instance, a travel assistant LLM could check flight prices, book tickets, and email confirmations. In enterprises, agentic LLMs might query databases or trigger workflows. The vision is to move from passive text generation to active, task-completing AI agents. How do LLMs support personalization? Personalization is where LLMs feel magical. By analyzing user history and preferences, they can adapt tone, complexity, and content. For example, an e-learning assistant can adjust lessons to a student's pace, while a shopping chatbot tailors recommendations. Even news summaries can be personalized, formal for executives, casual for teenagers. This makes interactions feel human-centered and relevant, boosting engagement and satisfaction. What is the role of LLMs in multimodal applications? Multimodal LLMs like GPT-4v handle not just text but images and soon audio and video. That means they can describe a photo, analyze a chart, or combine diagrams with text reasoning. In healthcare, they might analyze an X-ray alongside a doctor's notes. In education, they can turn visual diagrams into teaching explanations. Multimodality unlocks entirely new use cases, moving LLMs beyond text-only boundaries. What is LLM Ops and why is it important? LLM Ops is like DevOps for language models. It covers deploying, monitoring, and managing LLMs in production. Challenges include cost control, latency, prompt management, and compliance. For example, tracking hallucination rates or monitoring drift in outputs over time. As more businesses adopt LLMs ensures they remain reliable, scalable, and safe in real-world settings. Without it, production use of LLMs can quickly spiral into chaos. What are hallucinations in LLMs? Hallucinations are when an LLM makes things up confidently. For example, it might cite a non-existent research paper or fabricate statistics. This happens because the model predicts the most probable next word, not the truth. It's dangerous in high-stakes domains like healthcare or law. That's why hallucination control, via retrieval grounding, human review, or constrained generation, is critical for safe deployment. How can hallucinations be mitigated in practice? There's no silver bullet, but several strategies help. Retrieval augmented generation grounds answers in external sources. Lowering temperature makes responses less creative. Fine-tuning on factual, domain-specific datasets reduces fabrication. And in production, human-in-the-loop review catches critical errors. Together, these techniques minimize risk, ensuring LLMs produce trustworthy outputs rather than fluent misinformation. What are biases in LLMs and why are they concerning? LLMs inherit biases from their training data. For instance, if training data overrepresents men as CEOs, the model may repeat that stereotype. This is concerning in hiring, healthcare, or justice applications, where biased outputs can cause real harm. Mitigating bias requires balanced data curation, fairness-aware training, and monitoring. Ethical deployment means ensuring LLMs don't just sound smart, they act responsibly. How do LLMs pose risks to data privacy? Privacy risks come in two forms: training time memorization and runtime exposure. A model trained on raw internet data might memorize personal emails or credit card numbers. At runtime, users may paste sensitive data into prompts. Both scenarios risk leakage. Mitigations include differential privacy, redaction, and strict enterprise policies. In regulated industries like finance or healthcare, privacy protection isn't optional. It's a must. What is catastrophic forgetting and fine-tuning? Catastrophic forgetting is like a student who masters law but forgets math. When you fine-tune an LLM heavily on one domain, it can lose its general knowledge. For example, fine-tuning GPT for legal tasks might hurt its general conversation ability. Techniques like parameter-efficient fine-tuning LoRa, elastic weight consolidation, or mixing old and new data help prevent this, preserving broad capability while specializing. What are the biggest risks of deploying LLMs in production? Risks fall into three buckets: technical, ethical, and operational. Technically, costs and latency can spiral. Ethically, hallucinations and bias can harm users. Operationally, attacks like prompt injection pose new threats. Without guardrails, monitoring, filters, governance, deployments can backfire. Responsible LLM ops is about balancing innovation with safety so that models help rather than harm in real-world environments. Why is interpretability challenging in LLMs, and why does it matter? LLMs are black boxes with billions of parameters, making it hard to explain why they generate a specific answer. This is problematic in regulated domains, think finance, law, or medicine, where accountability is required. Techniques like attention visualization or probing give partial insights, but true interpretability is still an open challenge. It matters because without trust and explainability, adoption in critical industries will be limited. What is model distillation in LLMs? Distillation compresses a large model into a smaller one that mimics its outputs. The goal is efficiency, faster inference, lower memory, cheaper deployment. For example, a distilled version of GPT could power mobile devices or edge applications. While performance may drop slightly, distillation makes LLMs more accessible, scalable, and environmentally sustainable. It's a key step in democratizing AI. What are the most promising future directions for LLM research? The future is moving beyond bigger is better. We're seeing progress in multimodal models that handle text, images, and audio together. Personalization is another frontier, LLMs tailored to individuals without breaching privacy. Efficiency is critical, smaller, greener models that rival giant ones. And agentic LLMs, models that can reason, plan, and act, are gaining momentum. The trend is towards smarter, safer, and more useful models, not just larger ones. How will LLMs shape the future of work? LLMs will be co-pilots, not replacements. Doctors will have AI drafting clinical notes. Lawyers will have assistants scanning case law. Teachers will personalize lessons at scale. Developers already code faster with AI partners. The shift is from repetitive work to higher-order thinking, creativity, and strategy. LLMs won't take jobs wholesale, but they'll redefine how every knowledge worker operates in the next decade. What is the core innovation of the transformer architecture? The core innovation is the self-attention mechanism. Unlike previous models like RNNs that process text sequentially, self-attention allows the model to look at all the words in a sentence simultaneously and weigh their importance relative to each other. This enables parallel processing, which is crucial for training on massive data sets, and it allows the model to capture complex, long-range dependencies in language, making it the foundation of modern LLMs. What are emergent abilities and why are they significant? Emergent abilities are capabilities that appear in LLMs only after they reach a certain scale in parameters in training data. They are not present in smaller models. Examples include performing multi-step arithmetic or chain-of-thought reasoning. They are significant because they are not explicitly designed, but arise as a byproduct of scale, suggesting that simply making models bigger can unlock entirely new, unpredictable functionalities. Explain the concept of scaling laws in LLMs. Scaling laws describe the predictable relationship between a model's performance and the resources invested in it. Specifically, they show that as you increase the number of parameters, the size of the training dataset, and the amount of compute, the model's loss, a measure of error, decreases in a predictable power law fashion. These laws provide a roadmap for the industry, guiding decisions on how to allocate resources to build more capable models. What is tokenization, and why is an algorithm like byte pair encoding BPE used? Tokenization is the process of breaking down raw text into smaller units, or tokens, that the model can understand. An algorithm like byte pair encoding BPE is used because it's efficient and adaptable. It starts with individual characters and iteratively merges the most frequent pairs. This allows the model to handle any word, including rare or new ones, by breaking them down into known subword units, effectively balancing vocabulary size with sequence length. What is the purpose of positional embeddings in a transformer? The self-attention mechanism in a transformer is inherently order agnostic. It doesn't know the sequence of words. Positional embeddings are vectors that are added to the input embeddings to provide the model with information about the position of each token in the sequence. Without them, the model would treat the dog chase the cat and the cat chase the dog as having the same meaning, so they are essential for understanding grammar and syntax. Differentiate between an encoder-only and a decoder-only architecture. An encoder-only model, like BERT, is designed to understand context from both left and right, creating a rich representation of the input. It's ideal for analysis tasks like sentiment classification. A decoder-only model, like GPT, is autoregressive, meaning it generates text one token at a time based on what came before. It's built for generative tasks like writing articles or powering chatbots. What is transfer learning, and what is its role in LLMs? Transfer learning is a technique where a model is first trained on a broad, general task and then adapted to a more specific one. In LLMs, this is a two-stage process. First, the model is pre-trained on a massive corpus of internet text to learn general language patterns. Then, this knowledge is transferred and refined through fine-tuning on a smaller, task-specific dataset, making it a highly effective and efficient approach. What is a context window and what is its primary limitation? The context window is the maximum number of tokens an LLM can consider as input at one time. For example, a model with an 8K context window can process about 6,000 words. The primary limitation is computational cost. The self-attention mechanism's complexity scales quadratically with the sequence length. This means doubling the context window roughly quadruples the computation and memory required, making very long contexts expensive to handle. Explain the concept of a mixture of experts model. A mixture of experts is an architecture that uses a router network to dynamically select a small subset of expert networks to process each input token. Unlike a standard dense model where all parameters are used for every token, a MoE model only activates a fraction of its parameters. This makes training and inference significantly faster and more computationally efficient, allowing for models with a much higher total parameter count. How does a model learn from a self-supervised objective like next token prediction? In next token prediction, the model is given a sequence of text, and its only job is to predict the very next word. Since the correct answer is simply the next word in the text, the data provides its own labels, hence self-supervised. By performing this task billions of times on a vast data set, the model is forced to learn grammar, facts, context, and even reasoning patterns to make accurate predictions. What is reinforcement learning from human feedback? RLHF is a training stage used to align an LLM's behavior with human preferences. It involves 3 steps. First, fine-tuning a model on human-written examples. Second, training a separate reward model on human rankings of different model responses. Finally, using reinforcement learning to further tune the LLM, using the reward model's score as a signal to encourage helpful and harmless outputs. How does direct preference optimization, DPO, differ from RLHF? Direct preference optimization, DPO, is a more direct and stable alternative to RLHF. Instead of training a separate reward model and then using complex reinforcement learning, DPO uses the same human preference data, chosen versus rejected responses, to directly fine-tune the LLM itself. It reframes alignment as a simple classification problem, making it easier to implement and less computationally intensive. What is instruction tuning and why is it important? Instruction tuning is a form of supervised fine-tuning where the model is trained specifically on a data set of instructions and the desired responses. This process teaches the model to be a helpful assistant that can follow commands rather than just completing text. It's a critical step that transforms a base pre-trained model into a useful, interactive product like ChatGPT. Explain catastrophic forgetting in the context of fine-tuning. Catastrophic forgetting is a phenomenon where, during fine-tuning on a new task, a model loses some of the general knowledge and capabilities it learned during pre-training. As the model's weights are updated to specialize on the new data, they can overwrite the patterns that encoded its previous, more general knowledge. Techniques like PEFT are used to help mitigate this issue. What is parameter-efficient fine-tuning, PEFT? PEFT is a set of techniques for adapting an LLM to a new task without retraining all of its parameters. Instead, it freezes the vast majority of the model's weights and only trains a very small number of new or additional parameters. This drastically reduces the memory and computational costs of fine-tuning, making it possible to customize massive models on consumer-grade hardware. How does the LoRA, low-rank adaptation technique, work? LoRA is a popular PEFT method. It works by freezing the original model weights and injecting a pair of small, trainable, low-rank matrices into each layer. The fine-tuning updates are applied only to these small matrices. This dramatically reduces the number of trainable parameters. During inference, these small matrices can be merged with the original weights, adding no extra latency. When would you choose full fine-tuning over a PEFT method? You would choose full fine-tuning when you have a very large, high-quality data set, and the target domain is significantly different from the model's pre-training data. Full fine-tuning allows for a more substantial shift in the model's weights, which can sometimes lead to slightly better performance. However, this comes at a much higher computational cost and a greater risk of catastrophic forgetting. What is quantization and why is it used for LLMs? Quantization is the process of reducing the numerical precision of a model's weights. For example, from 32-bit floating point numbers down to 8-bit integers. This is done to significantly reduce the model's memory footprint and speed up inference. It's a crucial technique for deploying very large models on hardware with limited VRAM, often with only a minimal drop in performance. What is the role of a reward model in the RLHF process? The reward model is a critical component of RLHF. It's a separate model trained to predict which of two responses a human would prefer. During the reinforcement learning stage, the LLM generates an output, and this reward model provides a score, or reward, that reflects how good that output is according to human preferences. This reward signal guides the LLM to produce more helpful and less harmful responses. What is data contamination, and why is it a problem for evaluation? Data contamination occurs when the data used to evaluate a model is accidentally included in its training set. When this happens, the model's performance on a benchmark might appear very high, not because it has generalized well, but because it has simply memorized the answers. This gives a misleading and inflated sense of the model's true capabilities. What is perplexity as a metric for language models? Perplexity is a measure of how well a model predicts a given text sample. A lower perplexity score indicates that the model is less surprised by the text, meaning it assigned a higher probability to the correct sequence of words. It's a useful intrinsic metric for gauging how well a model has learned the statistical patterns of a language, but it doesn't measure factual accuracy or helpfulness. What are the main limitations of automated metrics like BLU and Rouge? The main limitation is that they rely on lexical overlap, counting how many words or phrases match between the model's output and a reference text. They fail to capture semantic meaning. A response could be perfectly correct and well phrased, but use different words, resulting in a low score. They are particularly poor at evaluating creativity, coherence, or factual accuracy. Why is human evaluation often considered the gold standard for LLMs? Human evaluation is the gold standard because qualities like helpfulness, coherence, creativity, and safety are subjective and nuanced. Automated metrics can't capture these qualities. Humans can assess whether a response truly answers the user's intent, is factually accurate, and adheres to safety guidelines, providing a much more holistic and reliable measure of a model's real-world performance. Name a common LLM benchmark and describe what it measures. A common benchmark is MMLU, which stands for Massive Multitask Language Understanding. It evaluates a model's general knowledge and problem-solving ability across 57 different subjects, including mathematics, U.S. history, law, and computer science. The questions are posed in a multiple-choice format, making it a broad and challenging test of a model's world knowledge and reasoning skills. How do temperature and top P sampling control model output? Both control the randomness of a model's generation. Temperature adjusts the probability distribution of potential next tokens. A low temperature makes the output more deterministic and focused, while a high temperature increases creativity. Top P sampling creates a pool of the most probable tokens whose cumulative probability exceeds a certain threshold P. This provides a more dynamic way to control randomness than just picking the top K tokens. How would you design an A/B test to compare two LLM-powered features? First, I would define a single, clear success metric like user engagement or a task completion rate. Then I would randomly assign users into two groups, a control group seeing the old feature, Model A, and a variant group seeing the new one, Model B. I would collect data over a set period, ensuring a sufficient sample size, and then use a statistical test to determine if the new feature provides a statistically significant improvement on the key metric. What is the difference between a benchmark and a red teaming evaluation? A benchmark, like MMLU, measures a model's capabilities on a standardized set of questions to gauge its performance and knowledge. In contrast, red teaming is an adversarial process focused on safety and robustness. A red team actively tries to break the model by finding prompts that cause it to generate harmful, biased, or unsafe content. The goal is to discover vulnerabilities rather than measure performance. What is a leaderboard in the context of LLMs? An LLM leaderboard, like the Hugging Face Open LLM leaderboard, is a public ranking of various language models based on their performance across a suite of standardized benchmarks. These leaderboards provide a way for researchers and developers to compare the capabilities of different models transparently. They drive competition and help track progress in the field, though they should be interpreted with caution as they don't capture all aspects of model quality. What are hallucinations in LLMs, and what is a primary cause? A hallucination is when an LLM generates information that is factually incorrect, nonsensical, or not grounded in the provided source data. A primary cause is that LLMs are pattern matching systems, not databases of facts. They generate plausible-sounding text by predicting the next most likely word based on their training data. If the patterns in the data are weak or contradictory, the model can easily invent details that sound correct but are entirely false. Describe a technique for mitigating bias in an LLM. One key technique is data curation. This involves carefully auditing the pre-training dataset to identify and remove or downsample content that contains harmful stereotypes and biases. Another technique is using RLHF, or DPO, with instructions that explicitly guide the model to be fair and impartial. By providing human feedback that penalizes biased responses, the model can learn to avoid generating them. What is model alignment, and why is it a critical area of research? Model alignment is the process of ensuring an LLM's goals and behaviors are consistent with human values and intentions, making it helpful, honest, and harmless. It's a critical area of research because as models become more powerful and autonomous, the risk of a capable but misaligned model causing unintended harm increases. Alignment ensures that this powerful technology is developed and deployed safely and beneficially. What is constitutional AI? Constitutional AI is a method for aligning a model with a set of desired principles or rules, known as a constitution. Instead of relying solely on human feedback to identify harmful responses, the model is prompted to critique and revise its own outputs based on the constitutional principles. This AI-generated feedback is then used to fine-tune the model, making it a more scalable way to instill desired behaviors like harmlessness. What is a major data privacy concern associated with LLMs? A major concern is that LLMs can inadvertently memorize and regurgitate personally identifiable information, PII, or sensitive data that was present in their vast training corpus. If a user's prompt happens to trigger a sequence similar to one containing private data from the training set, the model could expose that information. This necessitates careful data filtering and techniques to prevent such leaks. Explain the concept of dual use as an ethical risk for LLMs. Dual use refers to the risk that a technology designed for beneficial purposes can also be used for malicious ones. For LLMs, a model designed to be a helpful writing assistant could also be used to generate misinformation at scale, create phishing emails, or write malicious code. This requires developers to implement safeguards and monitor usage to prevent abuse. What is retrieval augmented generation, RAG? RAG is a technique that enhances an LLM's performance by connecting it to an external knowledge source. When a query is received, the system first retrieves relevant information from a database, often a vector database. This retrieved context is then provided to the LLM along with the original query, allowing the model to generate an answer that is grounded in specific, up-to-date, and verifiable information. When would you use RAG instead of fine-tuning a model? You would use RAG when your primary need is to provide answers based on a specific, rapidly changing, or proprietary body of knowledge. RAG is ideal for reducing hallucinations and allowing for source citation. You would use fine-tuning when your goal is to teach the model a new skill, style, or behavior that can't be easily conveyed through retrieved context, such as adopting a specific persona. What are LLM agents? What is their key capability? LLM agents are systems that use an LLM as a reasoning engine to perform complex multi-step tasks. Their key capability is tool use. An agent can break down a goal into a plan and then decide to use external tools, like a search engine, a calculator, or an API, to gather information or take actions in the world. This allows them to go far beyond simple text generation and interact with software and systems. What is the role of a vector database in a RAG system? A vector database stores information not as raw text, but as numerical representations called embeddings. In a RAG system, it plays the role of the knowledge library. When a user query comes in, it's also converted into an embedding. The vector database can then perform a highly efficient similarity search to find the chunks of text whose embeddings are closest to the query embedding, providing the most relevant context for the LLM. Explain chain of thought QOT prompting. Chain of thought prompting is a technique that encourages an LLM to solve complex reasoning problems by first generating intermediate steps. Instead of just asking for the final answer, you prompt the model to think step by step. This elicits a more deliberative reasoning process, often leading to more accurate results for tasks involving logic, math, or multi-step inference. What does it mean for an LLM to be multimodal? A multimodal LLM is one that can process and understand information from more than one type of data or modality. While traditional LLMs only work with text, a multimodal model like GPT-4o or Gemini can understand and generate content from a combination of text, images, audio, and even video. This allows for more natural and powerful human-computer interaction. What is speculative decoding, and how does it speed up inference? Speculative decoding is an optimization technique that uses a small, fast draft model to generate a chunk of several tokens. Then, a larger, more accurate verifier model checks this draft in a single, parallel step. If the draft is correct, it's accepted, saving the time of generating each token one by one. This can significantly increase the speed of text generation with minimal impact on quality. What is the attention head in a multi-head attention mechanism? In multi-head attention, the model doesn't just calculate attention once. Instead, it has multiple parallel attention heads, each of which learns to focus on different types of relationships in the text. For example, one head might track syntactic dependencies, while another focuses on semantic relationships. This allows the model to capture a richer and more diverse set of connections within the language simultaneously. How does flash attention optimize the self-attention mechanism? Flash attention is an algorithm that optimizes the self-attention mechanism by restructuring the computation to be more memory efficient. Instead of creating a large, intermediate attention matrix that needs to be read from and written to GPU high bandwidth memory, it uses techniques like tiling to keep computations within the much faster on-chip SRAM. This results in significant speedups and allows for processing longer context lengths. What is the difference between soft prompts and standard prompts? A standard prompt is a text string written by a human to guide an LLM. A soft prompt, used in a technique called prompt tuning, is a series of trainable embeddings that are prepended to the input. These embeddings are not actual words, but are learned by the model during training to steer its behavior for a specific task. It's a parameter-efficient way to adapt a model without changing its weights. What is the purpose of the feed-forward network in a transformer block? The feed-forward network, FFN, is a sublayer in each transformer block that is applied after the self-attention mechanism. Its role is to process the output from the attention layer on a per-token basis. It adds computational depth and introduces nonlinearity, allowing the model to learn more complex relationships and transform the token representations into a more useful form for the next block. What is the core idea behind the attention is all you need paper? The core idea is that you can build a high-performing sequence-to-sequence model using self-attention alone without needing any recurrent or convolutional layers. The paper demonstrated that the transformer architecture, based entirely on attention mechanisms, could achieve state-of-the-art results in machine translation while being more parallelizable and requiring significantly less time to train. This insight paved the way for modern LLMs. What is the lost in the middle problem for long context LLMs? Lost in the middle refers to the tendency of some LLMs with very long context windows to struggle with recalling or utilizing information that is placed in the middle of a long input document. The models often exhibit better performance on information located at the very beginning or very end of the context. This is a key challenge in making effective use of extended context windows. Why is fine-tuning on code data beneficial even for natural language tasks? Fine-tuning on code data can improve a model's performance on natural language tasks because code is highly structured and requires logical reasoning. Training on code forces the model to learn complex patterns, logical flow, and long-range dependencies. This can enhance its underlying reasoning abilities, which are then transferable to complex natural language problems that require similar skills. What is a key challenge in curating a high-quality pre-training dataset? A key challenge is deduplication and quality filtering. The internet is filled with redundant, low-quality, and toxic content. Building a high-quality dataset requires sophisticated pipelines to remove duplicates, filter out harmful or nonsensical text, and ensure a diverse and balanced mix of sources. Failure to do so can lead to a model that is repetitive, biased, and less capable. Where do you see the field of LLMs heading in the next 2 to 3 years? In the next few years, I expect to see three major trends. First, a move towards more efficient and smaller specialized models that can run on-device. Second, a significant improvement in multimodality, with models seamlessly integrating text, audio, and video. Finally, I anticipate a major focus on agentic capabilities, where LLMs will act as the brains for autonomous systems that can perform complex tasks and interact with software on our behalf. What is a large language model, LLM, and how does it differ from earlier NLP models? A large language model, or LLM, is a deep learning model trained on massive amounts of text to predict and generate human-like language. It's based on transformer architectures rather than older RNNs and LSTMs, enabling it to handle long sequences with self-attention. Compared to earlier NLP models that were task-specific, like models only for translation or classification, LLMs are general-purpose foundation models. This means they can perform multiple tasks like summarization, code generation, and reasoning, often without retraining, simply through prompting. Why are transformers the backbone of LLMs? Transformers introduce the self-attention mechanism, which allows a model to weigh the importance of all words in a sentence simultaneously, rather than processing them strictly in sequence as RNNs did. This leads to better context understanding, parallelization during training, and scalability to billions of parameters. That scalability is why transformers became the standard for LLMs like GPT, Claude, or LLAMA. Without transformers, we wouldn't have the computational efficiency or contextual accuracy that makes LLMs practical. What does pre-training mean in the context of an LLM? Pre-training is the stage where an LLM is exposed to enormous text datasets, books, articles, web pages, and code, to learn general statistical patterns of language. The task is usually next token prediction. The model learns to guess the next word based on context. Through this, the model captures grammar, semantics, factual knowledge, and reasoning templates. Pre-training creates a broad foundation of knowledge, which can later be specialized through fine-tuning or prompting for specific domains, such as medicine, law, or software development. How does tokenization affect LLM performance? Tokenization is the process of breaking text into smaller units, called tokens, that the LLM can process. A token may be a word, subword, or character, depending on the tokenizer. Efficient tokenization, like byte pair encoding, balances granularity and performance, ensuring that the model understands rare words while not exploding the vocabulary size. It directly affects training speed, memory efficiency, and how well the model handles different languages. Poor tokenization can lead to inefficiencies, higher costs, and degraded output quality. Why are LLMs referred to as foundation models? They're called foundation models because they serve as a flexible base that can be adapted to many downstream tasks. Just like a building foundation can support diverse structures, an LLM's pre-trained knowledge can power a wide variety of use cases: chatbots, copilots, summarizers, or retrieval systems with minimal adjustments. This foundation aspect makes them more efficient and scalable compared to building separate models for each task. What is the typical training pipeline of an LLM? It usually has two major stages: pre-training and fine-tuning. During pre-training, the model learns general language patterns from large data sets. Fine-tuning, or alignment, is the second phase, where the model's outputs are adjusted to meet real-world needs, like being polite, accurate, or domain-specific. This might involve supervised fine-tuning, reinforcement learning from human feedback, RLHF, or parameter-efficient methods like LoRa. Together, these stages create models that are broad in knowledge but safe and useful in specific deployments. What is RLHF, and why is it essential to modern LLMs? RLHF stands for Reinforcement Learning from Human Feedback. It's an alignment technique used after pre-training. Humans first rank model outputs by preference, creating a reward model. Then, reinforcement learning optimizes the LLM to match those preferences. This step is critical because raw LLMs are often unfiltered. They might be factually wrong or unsafe. RLHF guides them to be more aligned with human values, producing outputs that are more helpful, safer, and appropriate in real-world applications. Explain the role of attention heads in transformers. Each attention head in a transformer learns to focus on different patterns of relationships between tokens. One head might track syntactic dependencies like subject-verb agreement, while another identifies semantic relationships like synonyms. By stacking multiple heads in parallel, the model captures rich, multidimensional context. This multi-headed mechanism is what gives LLMs their nuanced language understanding, and it scales efficiently when dealing with complex inputs. What are the challenges of scaling LLMs to billions of parameters? The bigger the model, the more compute, memory, and energy required to train and deploy it. Training large models like GPT-4 costs millions of dollars and takes extensive GPU clusters. Inference cost also rises because larger models are slower and more expensive to serve. There are also diminishing returns. Doubling parameters doesn't mean doubling performance. To address this, researchers focus on efficiency innovations like quantization, distillation, and mixture of experts. What is parameter-efficient fine-tuning, PEFT? PEFT is a set of techniques to adapt LLMs for specific domains without updating all their billions of parameters. Methods like LoRa, prefix tuning, or adapters add small layers or low-rank updates, fine-tuning only a fraction of the model. This reduces training costs, storage needs, and deployment overhead, while still achieving strong task specialization. It makes fine-tuning feasible even for smaller organizations without massive infrastructure. How is inference optimized in LLMs? Inference is optimized using a mix of software and hardware strategies. On the hardware side, specialized accelerators like GPUs and TPUs, along with batching, speed up token generation. On the model side, techniques like quantization reduce precision from 32-bit to 8 or 4-bit, greatly lowering memory and compute. Distillation helps compress models while keeping performance. Another important optimization is caching past key-value attention states during autoregressive decoding, which saves redundant computation. This combination makes running large LLMs much faster and affordable in real-world applications. Why does context length matter in LLMs? Context length defines how many tokens the model can see at once. A model with only a few thousand tokens might lose context in long conversations or documents. Extending context length, as in GPT-4 or Claude, allows the model to handle entire research papers, legal documents, or hour-long transcripts without forgetting earlier details. This enhances reasoning continuity, but also raises computation and memory costs, since attention scales quadratically with context length. Efficient context scaling methods are an active research area. What is the role of embeddings in LLM-based systems? Embeddings are vector representations of text segments generated by LLMs or separate embedding models. They capture semantic similarity, phrases with similar meaning map close in vector space. This makes them vital for retrieval augmented generation RAG, where embeddings index knowledge bases for quick, context-relevant lookups. They are also used in semantic search, clustering, recommendation, and personalization. In short, embeddings turn raw text into machine-understandable numerical form essential for downstream NLP and retrieval tasks. How does distillation make LLMs more efficient? Distillation is a process where a small student model learns to mimic the output behavior of a large teacher, LLM. Instead of training the small model from scratch, it's guided by the larger model's responses, leading to compact yet performant models. Distilled models are more efficient in deployment, faster inference, and lower memory use. making them suitable for edge devices or cost-sensitive deployments. While they may lose some generality, distillation balances capability and practicality. Can you explain mixture of experts, MOE architecture? MOE models divide computation among specialized subnetworks experts, with only a few experts activated per input. For example, instead of processing every input through all 500 billion parameters, the model selectively chooses the most relevant experts. This allows for very large capacity while keeping runtime efficient. Google's switch transformers use this approach. MOE models reduce computation cost and allow modular scaling, but they also add challenges in balancing training and routing the right expert effectively. How are LLMs applied in enterprise knowledge management? Enterprises use LLMs for tasks like document summarization, question answering, and drafting reports. By integrating LLMs with internal data through retrieval-augmented generation, employees can query their private documents conversationally. Customer support chatbots, contract review assistants, and research copilots are typical use cases. Enterprises often fine-tune or align LLMs to their domain to ensure accuracy, compliance, and privacy. This allows for huge productivity gains while maintaining trust and control over corporate data. How are LLMs utilized in programming and software engineering? LLMs trained on code repositories power tools like GitHub Copilot or Code LLM. They assist with code auto-completion, bug detection, unit test generation, and documentation. They simplify the development process by translating natural language queries into functioning code in multiple languages. They don't just auto-complete, they help developers explore unfamiliar libraries, accelerate prototyping, and even refactor code. However, developers must verify outputs since hallucinations in code can introduce subtle bugs or security issues. What is retrieval augmented generation, RAG, and why is it important? RAG is a framework where an LLM is combined with an external knowledge retriever. When a user asks a question, the retriever pulls relevant documents or passages, which are fed into the model's context before generating the answer. This reduces hallucination by grounding responses in real, updated knowledge rather than just pre-trained memory. It makes LLMs usable in domains requiring factual accuracy, such as healthcare, law, or finance. RAG is the backbone of many enterprise AI solutions today. How do LLMs support multimodal AI applications? Multimodal LLMs can process text alongside images, audio, or video. For example, GPT-4 Vision interprets images in combination with text, enabling applications like image captioning, document analysis, and visual question answering. When combined with speech input and output, multimodal LLMs enable end-to-end assistance that can see, hear, and converse. The integration of modalities makes them useful in accessibility, robotics, creative tools, and scientific analysis, moving AI closer to general-purpose intelligence. How are LLMs advancing education applications? In education, LLMs power personalized tutors, automatic grading assistants, and study aid generators. They can generate practice questions, adapt explanations for different learning levels, and summarize complex readings. By integrating with curricula, they provide interactive support to both students and teachers. For instance, a student struggling with math could get step-by-step coaching, while teachers can automate lesson plans. The key challenge is to ensure accuracy and alignment so that learners receive reliable guidance. What are hallucinations in LLMs and why do they happen? Hallucinations occur when an LLM generates content that is fluent and confident, but factually incorrect or fabricated. They happen because LLMs don't have a built-in grounding mechanism. They predict text based on statistical patterns, rather than verifying information against a fact base. During pre-training, the model learns correlations, not truth. So in unfamiliar contexts, it may invent details rather than say, "I don't know." This risk makes hallucinations especially dangerous in fields like healthcare or law, where accuracy is non-negotiable. How can data bias affect the reliability of an LLM? LLMs learn from massive data sets that often reflect human biases around gender, race, culture, or ideology. If unaddressed, these biases can be reproduced or even amplified in output. For example, biased hiring data might cause an LLM to favor certain demographics in resume screening, Bias undermines fairness, leads to reputational risks, and can cause real-world harm. To mitigate this, practitioners use better curation of training data, adversarial testing, fairness constraints, and auditing frameworks. What is prompt injection, and why is it considered a major security risk? Prompt injection is when malicious users craft inputs that trick the LLM into ignoring its instructions or exposing sensitive data. For instance, an attacker might embed hidden instructions to override content filters or extract confidential system prompts. This makes LLMs susceptible to jailbreaks and data leakage. Mitigation strategies include strong input sanitization, layered filtering, structured prompt isolation, and using external policy enforcement tools. It's a critical risk for enterprise deployments. How do companies mitigate ethical risks of LLM deployment? Ethical risk mitigation requires a multi-layer approach. First, ensuring diverse and representative training data reduces bias. Second, applying alignment methods like RLHF or constitutional AI improves safety. Third, companies implement monitoring systems to flag inappropriate output. Human-in-the-loop review remains critical for high-stakes use cases. Finally, transparency about model limitations, user education, and regulatory compliance ensures responsible AI adoption. It's a balance between technical safeguards and governance. Why is privacy a concern when deploying LLMs in enterprises? LLMs process sensitive user inputs, which can include confidential business data or personal information. If prompts are sent to third-party APIs, privacy risks increase. Additionally, LLMs may memorize training data and inadvertently output private details. Enterprises address this with on-prem deployments, fine-tuning smaller private models, encryption in transit, anonymization, and confidential computing. Privacy isn't just regulatory, it's also about maintaining customer trust when leveraging LLM capabilities. How do open-source LLMs like Llama differ from proprietary ones like GPT-4? Open-source models like Llama, Falcon, and MPT provide transparency, customization, and lower deployment costs since organizations can fine-tune them in-house. Proprietary models like GPT-4 and Claude often lead in the capability, safety, and tooling, but are closed source with higher costs and possible vendor lock-in. The choice depends on trade-offs between performance needs, privacy requirements, and budget. Many enterprises adopt a hybrid model, proprietary APIs for high-value tasks and open source for private workflows. Why is domain-specific fine-tuning increasingly important? General-purpose LLMs are broad but shallow in expertise. Enterprises need models tuned to specialized knowledge, such as medicine, finance, or legal reasoning. Fine-tuning on domain data improves accuracy, compliance, and trustworthiness. For example, a medical LLM can flag adverse drug interactions more reliably than a general model. Domain fine-tuning bridges the gap between broad capability and real-world utility, allowing businesses to deploy relevant, customized AI solutions. How are LLMs being integrated into AI agent architectures? In agent-based systems, the LLM acts as the reasoning core, interpreting user input, planning tasks, and making decisions. Agents then connect LLMs to external tools, APIs, or databases, enabling actions like booking flights, retrieving enterprise documents, or doing financial analysis. Frameworks like LangChain or AutoGPT demonstrate this. LLMs provide the intelligence, while agents provide the execution layer. This combination moves AI from being a conversational tool to an autonomous problem solver. How do LLMs compare to smaller, fine-tuned models in production? Large models have broad generalization and excel at open-ended tasks, but they are expensive and resource-heavy. Smaller models, when fine-tuned effectively, can outperform LLMs on narrow domains while being cheaper and faster to deploy. For instance, a lightweight legal chatbot, fine-tuned on contracts, may beat GPT-4 in accuracy for that domain. The trend is toward hybrid ecosystems, foundation LLMs for general reasoning, and specialized smaller models for specific enterprise tasks. What major trends will shape LLM development in the next 5 years? Looking forward, we'll see 3 major trends. 1. Multimodality, with models reasoning across text, images, audio, and video. 2. Longer context handling. the model's processing entire databases or conversations seamlessly. And 3, agent integration, where LLMs combine with tools to act, not just predict. Efficiency will also be critical. Parameter-efficient fine-tuning, quantization, and edge deployment will make LLMs accessible beyond large tech firms. Overall, the shift is from raw generative power toward grounded, safe, and personalized AI systems. What is chain of thought, COT, prompting, and its significance? Chain of thought prompting encourages the LLM to generate intermediate reasoning steps before giving a final answer. For example, instead of directly answering a math problem, the LLM outlines its step-by-step logic. This improves accuracy in multi-step reasoning tasks. It's particularly powerful in domains like math, logic puzzles, or structured decision-making. While COT improves reasoning accuracy, it can also increase latency and token cost, so it must be balanced with performance needs. How do long context models overcome attention bottlenecks? Standard self-attention scales quadratically with context length, making it expensive for very long prompts. Long context models overcome this with innovations like sparse attention, linearized attention, or segment recurrence. For example, models like Claude 2 extend to 100K tokens, using more efficient architectures. These allow entire books, legal records, or transcripts to be processed without truncation. Innovations here unlock use cases in research, law, and enterprise archives that demand sustained memory. What is in-context learning and why is it special? In-context learning is the ability of LLMs to adapt to a new task just by seeing examples in the prompt, without changing model weights. For instance, if you provide 3 examples of translating English to Spanish in a prompt, the LLM learns to continue the task. This is significant because it removes the need for task-specific fine-tuning, enabling flexible use of a single model across many domains with only prompt engineering. How does quantization make models deployable at scale? Quantization reduces the precision of model weights, for example, from 32-bit floating point to 8-bit or even 4-bit integers. This drastically reduces memory footprint and speeds up inference while keeping model performance close to original. For enterprises, this means faster, cheaper deployments on commodity hardware instead of specialized GPU clusters. Quantization enables edge deployments as well, where smaller devices can run LLMs locally for privacy-sensitive tasks. Can you explain catastrophic forgetting in LLM fine-tuning? Catastrophic forgetting occurs when fine-tuning on a narrow dataset overwrites the broad general knowledge the model learned in pre-training. For example, adapting an LLM to legal language might cause it to lose performance on general conversation tasks. This is problematic when the same model is reused across contexts. Solutions include parameter-efficient fine-tuning, updating smaller subsets of weights, or multitask training that mixes domain data with general examples to preserve balance. How are LLMs evaluated for quality? Evaluating LLMs requires both automated and human-centered metrics. Automated measures include perplexity, BLEU, or Rouge for text quality, and task accuracy on benchmarks like MMLU for reasoning or HELM for general robustness. However, these don't capture subjective aspects like helpfulness or safety. Human evaluations are necessary for clarity, correctness, and alignment. Many organizations now combine crowdsourced ratings, domain experts, and red team testing for comprehensive evaluation. What does perplexity indicate in language modeling? Perplexity measures how well a language model predicts text sequences. A lower perplexity indicates the model is assigning higher probability to the actual observed text, meaning it understands the language patterns better. While useful during training, perplexity is not always predictive of real-world conversational quality. A model with low perplexity can still hallucinate facts. So perplexity is one tool among many and should be complemented with task-specific performance metrics. Why is evaluating reasoning in LLMs challenging? LLMs don't think as humans do. They generate text patterns. Evaluating reasoning is challenging because fluent responses can appear logically sound, even if wrong. Benchmarks may favor memorization instead of genuine reasoning. Chain of thought prompting and adversarial tests expose reasoning gaps, but no definitive metric exists. This makes human question design critical. For example, testing consistency across variations of logically equivalent problems to ensure the model isn't just guessing. What is adversarial testing for LLM robustness? Adversarial testing deliberately stresses the LLM with tricky or malicious prompts to uncover weaknesses. This might include attempts to circumvent safety filters, trick the model into contradictions, or provoke harmful content. By exposing vulnerabilities, developers can patch them before real-world deployment. It's like penetration testing for cybersecurity, applied to language models. Adversarial testing is now standard practice in organizations deploying LLMs safely. How do human evaluations complement automated metrics? Automated metrics like perplexity or BLEU only measure surface-level text similarity. They don't capture nuances of helpfulness, style, or ethical alignment. Human evaluations fill this gap by judging qualities like clarity, factual correctness, and relevance. Combining both approaches ensures balanced evaluation, automated metrics for scalability, and human evaluations for real-world quality. This dual evaluation framework is essential for LLM deployment in high-stakes scenarios. What infrastructure challenges exist in deploying LLMs? Deploying LLMs at scale is extremely resource-intensive. First, inference requires powerful GPUs or TPUs due to billions of parameters, driving up costs. Second, latency can be high because generating text is sequential. Each token depends on the last one. Third, memory demand is massive. Even storing models requires hundreds of gigabytes. Additionally, serving concurrent requests for thousands of users requires load balancing, caching, and distributed inference. Organizations also face challenges in data security, monitoring, and scaling infrastructure to maintain consistent performance. How do orchestration frameworks like LangChain help? Frameworks like LangChain simplify building applications on top of LLMs by acting as orchestration layers. They connect the LLM to external tools such as databases, APIs, or retrieval engines, enabling things like RAG pipelines or AI agents. Instead of manually handling prompts, memory, and multi-step workflows, LangChain provides abstractions for chaining tasks together. For enterprises, this reduces complexity, accelerates development of LLM-powered applications, and standardizes best practices around tool use, grounding, and safety. Why are embeddings critical for enterprise search solutions? Embeddings transform text into vectors, allowing semantic similarity search rather than keyword-only search. In enterprise systems, this means employees can retrieve documents based on intent, even if specific keywords are absent. For example, asking budget forecast could retrieve documents titled financial projections. When paired with RAG, embeddings allow enterprises to ground LLMs in private data. Without embeddings, knowledge retrieval would be brittle and incomplete, limiting the usefulness of LLM-driven search solutions. How do companies ensure compliance in LLM deployment? Enterprises ensure compliance by controlling what data gets fed into LLMs and how outputs are monitored. This means filtering sensitive data, anonymizing inputs, and setting strict access controls. They also include audit logs to trace how the model was used. Regulatory frameworks like GDPR or HIPAA require that user data isn't misused or persisted. So many companies deploy LLMs on premises or in private clouds. Ongoing monitoring, legal review, and alignment with AI ethics guidelines further safeguard compliance. What makes fine-tuning large LLMs cost-prohibitive? Full fine-tuning requires updating billions of parameters, which means massive GPU clusters, high energy use, and long training cycles, sometimes costing millions of dollars. Storage also becomes difficult since every fine-tuned model copy could be hundreds of gigabytes. This makes frequent customization impractical. That's why parameter-efficient fine-tuning methods like LoRa or adapters are gaining adoption. They reduce costs dramatically, allowing organizations to fine-tune models with far fewer resources while keeping most of the base model intact. What is constitutional AI and how does Anthropic use it? Constitutional AI is a technique developed by Anthropic to align LLMs more safely. Instead of relying only on human feedback, the model is trained using a constitution, a list of principles that guide its behavior. The model critiques and revises its outputs according to these rules, learning to self-align with ethical standards such as harmlessness, helpfulness, and honesty. This reduces dependence on human labelers and improves consistency. It makes the LLM more predictable, transparent, and ethically governed compared to traditional RLHF alone. How do GPT-4, Claude, and Gemini differ strategically? Each reflects its company's priorities. OpenAI's GPT-4 focuses on general-purpose capability and developer-friendly APIs, powering ecosystems like ChatGPT and Microsoft Copilot. Anthropic's Claude emphasizes safety, built around constitutional AI, making it attractive where ethics, governance, and risk management are critical. Google's Gemini is integrated deeply with search and multimodality, excelling at reasoning across text, images, and possibly video. The competition isn't just on raw power, it's also about positioning. OpenAI for capability, Anthropic for safety, and Google for integration with consumer and enterprise platforms. What are some examples of LLM use cases in healthcare? LLMs in healthcare assist with drafting medical notes, summarizing patient histories, and converting jargon into patient-friendly explanations. They also support literature review by synthesizing research papers, accelerating drug discovery. For clinicians, copilots help with form completion and compliance documentation, reducing admin burden. At the same time, LLMs must be carefully supervised to avoid hallucinations or unsafe recommendations, as patient safety is paramount. So their role is assistive, augmenting doctors rather than replacing them. What are AI copilots and why are enterprises adopting them? AI copilots are domain-specific assistants built on top of LLMs, integrated directly into productivity or workflow tools. For example, GitHub Copilot helps developers write code, while Microsoft 365 Copilot assists with office tasks like drafting emails and presentations. Enterprises adopt them because they improve efficiency by automating routine work and enhancing creativity. Copilots also leverage internal data through RAG, making them context-aware. They represent the shift from standalone chatbots to embedded assistants across enterprise ecosystems. Do LLMs truly reason, or are they pattern matchers? LLMs don't reason in the human sense. They don't understand concepts consciously. Instead, they're advanced pattern matchers, predicting the most likely sequence of words based on training data. However, because reasoning itself is often expressed as patterns in language, LLMs can simulate reasoning convincingly. With techniques like chain-of-thought prompting or integration with external tools, they can solve problems step by step, appearing intelligent. So while it's not true reasoning, it's a powerful approximation that can be extremely useful in practice. You've just gone through 150 of the most important LLM interview questions and answers, the exact kind of preparation that gives you an edge in generative AI interviews. If this video helped you, make sure to like, share, and subscribe so you never miss future AI prep content. Thanks for watching, and remember, the future of AI careers belongs to those who prepare today.